Any questions? طيب يعني everything is clear. واضحة الأمور. جاهزين للكويز. Alright. Let's continue with the multiplexer. We started last time to discuss another example on combinational logic circuits, which we call the multiplexer, or simply the MUX. And we said that the MUX is a circuit that has a set of inputs. We call them the data inputs and one output. And basically, this circuit passes one of the inputs to the output based on our selection. بيعتمد what input do we select? We feed the number, the input number on the selection lines. We call these the selection lines. When we do that, we are basically selecting one of the input to appear at the output. So we saw how to design such a circuit, and we started from the smallest MUX, which is the 2-to-1. We designed it the conventional way. Then we moved and we designed bigger multiplexers in two approaches. The first approach by noting what is inside the 2-to-1 MUX, which is 1-to-2 decoder, 2 AND gates, and 1 OR gate, if you remember. And the other one was basically building big multiplexers using smaller ones. So that's what we discussed basically in the first lecture on the multiplexer. Then last lecture, we started to talk about the one application of the multiplexers. And I said last time that this is not the main purpose why we invented multiplexers. Multiplexers, as the name implies, they are used for multiplexing or for data selection or for sharing, to share something. And this is clear here. We have a single output that is shared between multiple entities or multiple inputs. However, we said there is one basic application that we can use the multiplexer for, which is to implement logic functions. For example, we said if we have a function of two variables, A, B, and this is F. So this is a function of two variables. We have 4 possible combinations. Let's say this is 0, 1, 1, 0. So this is a function of A, B. We said we can implement this circuit or this function using multiplexer. Only one component, which is a multiplexer. And the size of the multiplexer that we need is basically, what is the size of the MUX to implement this function?
4-to-1.
How many choices do we have for the function? We said 4, was what? So we said basically we need a device through which we can select one of these possibilities to appear for the function. So we need 4 choices. We need 4-to-1 multiplexer. So this is a 4-to-1 MUX. The selection line S1, S0. The data lines input 0, input 1, input 2, input 3. And this is the output. So basically the output of the MUX is the function f of AB. And the selection lines are basically the input variables, because through these variables, we select which output to appear, which value to be assigned to the function, whether it is 0, 1, 1, or 0. So these values, the input variables, they decide. So how do we select between these inputs using these variables? How do we select, for these one of these outputs to be assigned to the function using the input variables? How do we select one of the data inputs to appear at the MUX output? Basically through the selection line. So what we did here is we connected A and B to the selection line in order to select one of these values. So if I input here 0, 0, so this is the input, so the output should be 0. The function should be 0, so it has to be connected to 0. Input number 0 has to be connected to 0. The same thing here, here, here. So we discussed that last time. 4-to-1 MUX. So this is what is needed in order to implement this function. So I called this method 1. If you remember, we called it method 1, which is to implement a logic function using a multiplexer of a suitable size. So basically, what is needed if we have an invariable function, what do we need to implement an invariable function? Basically, we need 2 to the power n to 1 max, right? And next, we connect the input variables. I think we wrote that last time. Input variables to the select lines, as we did here. The function is basically the output. So this is, we need this max, a max of this size. We need to connect the input variables to the select lines of the multiplexer. And the last thing is basically to fix the data inputs of the multiplexer to according to the truth table, or to match the truth table. We wrote it that last time. So it is as simple as that. However, we said that using this method is straightforward. However, as the size of the function or the number of variables increase, the size of the multiplexer will increase exponentially. So for example, if we have a function of 2 variables, we will need 2 to the power 2 inputs. So we need 4 to 1 max, right? Now, if we increase the variables by 1, so we will have 3 variables. So the number of combinations will be 8. So the size of the inputs, the number of the inputs will be 2 to the power 3, which is 8. 4 variables, we need 16. And so on. So as the number of variables increases, the size of the multiplexer in terms of the number of inputs increases exponentially. And this will be expensive, despite the fact of being a straightforward and easy way to implement the functions. So the idea here, how we can still implement, how we can reduce the size of the multiplexer, but at the same time, be able to implement the logic function. So the basic idea, we want a method or some approach that uses multiplexers to implement logic functions. However, it uses smaller multiplexers. It uses smaller multiplexers. What is this approach? So basically, this is method, I call it method 2. So let's take the same function, AB F0110, which is basically an XOR gate if you look carefully. So this is our function from the previous example, and we implemented using 4 to 1 multiplexer. Can we implement this function? Can we implement F using, let's say, 2 to 1 max?
دكتور، لأنه لما نختار الزيرو عند A فالأوتبوت هو نفس B، أما لما يكون 1 هو عم بيكون B complement، فممكن نعمل هذا الشيء.
يعني مضبوط يا رند. يعني هلا لو أنا جبت 2 to 1 max, input 0, input 1, and this is the output, which is basically the function of AB. Now, I have a problem. I have 2 choices or 2 inputs in the multiplexer, but I need 4 because I have 4 choices for the function values, either this value or this value or this value or this value, based on the input value, How can I map 4 inputs or 4 possible combinations to 2 possible selections? At the end of the day, I need to perform selection. I need to select something, and what I can select here is basically 1 out of 2 instead 1 out of 4. So what to do? There basically is we divide the table into 2 sections in order to be able to select 1 out of 2, because we have 2 choices, so we can only select 1 out of 2. So we divide the table into 2 sections, and if we divide it the way that I did here, basically I am using variable A. I am using variable A to divide the big truth table into 2 smaller truth tables, if you like, or 2 sections, as we did when we constructed big multiplexers from smaller ones and big decoders from smaller ones. And this section is basically has the same value for A, and this section has the same value of A. So if I connect A here, so what is the idea here? If A is 0, this implies that I am in the first section of the table, in the top section of the table. If A is 1, the operation is in the lower section or in this section of the table. So if I select this section, then I'm selecting this input. So if A is 0, I'm selecting this input. What is the function when I select this section? Basically, if we look, we can write F is basically B. If you look here, F is basically the same as B. It is B. So this is a function of one variable. I'm trying to express F in terms of the remaining variables. I used A to split the table into 2 sections, and then I used the remaining variable or variables to express the function in terms of them. So here we have, if AB is 0, then F is 0. If B is 1, then F is 1. The same thing, when A is 1 here, I'm selecting this input. So I am operating in this section. What is the relation between F and B here? F equals B bar. F is basically B bar. So what should I connect here? I connect here B, right? And then I need here to connect B bar. Is this correct? Let's try. If the input is 0 and B is 0, the output is 0. So if the input is 0, I am selecting this. If A is 0, I'm selecting this input. And if I select this input, what will appear on the function here? B. And what is the value of B? It is 0. If this is 0 and B is 1, the function should be 1. So if this is 0, I am selecting this input. وبالتالي F is basically B, and B is 1, so the function will be 1, and so on. So this is basically how we implement the function. Basically, we use, because we have a smaller multiplexer, we can do fewer selections. Instead of doing 1 out of 4 selections here, we can only do one out of 2. So how can we do that if we have 4 options? So basically, we group the options. We say we either select this or we select this section. So we are, instead of selecting rows, we are selecting sections. And to do that, we use the most significant variable or variables, depending on the size of the function. And what is next? Basically, we use the remaining variables to express the function in each section, as we did here. Then we connect them as we saw here. Now, look, if we look carefully here, we were able to reduce the size of the multiplexer from 4 to 1 to 2 to 1. And this is very effective because this, if you go back to what we discussed at the beginning, what is inside this mux? هذا الماكس في جواته 2 أو 1 to 2 decoder مظبوط، في جواته 2 AND gates، وفي جواته 2 input OR gate صح؟ طيب ال 4 to 1 what is inside the 4 to 1 it is 2 to 4 decoder 4 2 input AND gates و 4 input OR gates مظبوط. So this is much expensive than this one in terms of the number of gates. But what is the cost of using a smaller multiplexer? Basically, you may need, this is very important, you may need to add or to use an inverter. Depending on the function, you might not need an inverter. You may need an inverter. So basically, method number 2, in order to implement a function, an invariable function using multiplexer of smaller size, we can implement it using 2 to the power n minus 1 to 1 max. So the size of the multiplexer is halved. It is half of the one we used in method number 1. Then what did we do? Connect the n minus 1 most significant variables to the select lines. That's what we did here. The most significant variable, we have only one variable here because we need one variable because we splitted the table into 2 sections, so we need one variable. So, however, as we will see in the coming example, we may need to split the table into more than 2 sections, depending on the size of the function and the size of the multiplexer. And the last step basically is express for each section, express the function in terms of the remaining variables. وفي هذه الحالة we have only B. So the remaining variable, after we used A to split the table, we use the remaining variable. In this case, we have only one variable to express the function in terms of the remaining variables. So very simple. And you can extend it to method 3, to method 4, to method 5, which is basically you keep decreasing the size of the multiplexer. However, in this case, you will start to use more variables, more of the least significant variables to express the function, and you will need more than an inverter. You will need maybe an AND gate, an OR gate, an XOR. So let's take 2 or what's the time? Yeah, 2 examples. We're running out of time. So let's take 2 examples. Assume we have function f of a, b, c is sum of minterms 1, 3, 6, and 7, and we want to implement it using multiplexer. And we have many choices. So let's assume we want to implement using method 2. Method 2 implies that n here is 3. The number of input variables is 3. So we will need 2 to the power 2 to 1 max, which is basically 4 to 1 max. And possibly we might need an inverter or a NOT gate. We might need an inverter depending on the function. So in order to implement this function, we will need the truth table. So A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. So this is these are the combinations, and this is F, which is minterm 1, minterm 3, minterm 6, and 7. So this is the truth table, and we have what we have here is 4 to 1 mux. 4 to 1 mux. So we have input 0, input 1, input 2, input 3, and the function f. This is S1, S0. So what to do here? As we said, we have 80 choices to select from, but we only have the ability to choose from 4 choices. So what to do? Basically, we divide the table into 4 sections. So we say this is one section, this is another section, and in order to select one out of these 2 sections, we need 2 variables. So we use the n minus 1. What is n? N is 3. So we use 2 most significant variables. We use 2 most significant variables to split the table into, in our case, 4 sections. This is the first section. They have the same values for A and B. Each section we have the same value for A and B. So this is section 1, section 0, I'm sorry, section 1, section 2, and section 3. But what is, how to reflect this on the circuit? So this is basically A, and this is B. This is A, and this is B. We connect the most significant, the n minus 1 most significant variable to the select lines. And what is next? Express the function in terms of the remaining variable. So what is f in terms of c here? If c is 0, f is 0. If c is 1, f is 1. So this is f equals c. The same thing here, it is f equals c. And here we have, regardless of c, the function is always 0. So this is f equals 0, f equals 1. Regardless of c, the function is always 1. So now we say if we have 0, 0 here, then we are operating in this section, and in this section the function is c. So 0, 0 implies we are selecting this input, so we have to connect this input to c. The same thing, section number 1 is when we place 0, 1 here. So we select this input, and in this input the function should be c, and same thing here, 0 and 1. 0 and 1. So if you look here, we were able to use a 4 to 1 mux instead of the 8 to 1 mux that we need to use if we picked or we choose method number 1. The second thing, we did not need an inverter because the expressions that we got for the function in each section does not need an inverter. Okay, none of the sections requires an inverter. Here we have C, 0, and 1. Okay, so that's why we said we might need an inverter in method number 2. So this is the basic idea. To use a multiplexer with half the number of inputs when compared to method number 1, we might need an inverter. And we need to split the table using the n-1 variables, as we did here. Then we specify the function in terms of the remaining variable, like what we did here. Okay? Now, as I said, you can extend this further. Can we reduce the size of this mux, for example, to 2 to 1 mux? So if you want to call this method number 3, can we reduce the size of the mux further?
بالضبط. بالبداية رح يكون في عندي سي، وآخر اثنين رح يكونوا زي 1 بار أو 0 بار.
احكي لنا كيف يا رند. نفس المبدأ صح؟
لما يكون بدنا نختار 0 فرح يكون f بيساوي سي نفس الشيء.
ماشي، يعني شو الفكره اللي سويناها احنا؟ زي الفكره اللي هون، يعني انا الان زي ما حكينا using the multiplexer to implement this function I need 8 to 1 multiplexer because I have 8 choices. مظبوط. But when I had only a hardware that supports 4 choices, I needed to express the inputs in terms of the remaining variable. طيب now I reduced the size of selections in the hardware to 2 selections only while I have 8. What does this imply? I will need to split the table into 2 sections, and to do that using how many variables do I need to split into 2 sections? I will use only one variable which is the most significant variable. في عندنا هون ال A هي 0 وال A هون هي 1. فإذا هي A على selection line to select whether we are working here or we are working here. طيب, if A is 0, we need to find an expression for F in terms of the remaining variables. It's not one variable now, it is variables which are B and C. What is the expression for F in terms of B and C in this section? You need to simplify it, okay? But if you do that, as Rand said, you will see that F is basically C. If you simplify F in terms of B and C using the map, you will find that this is C. And here you will find that what is the function in terms of B and C. If you look carefully, you will see that F is B in this section, F is B, and in this section, F is C, basically. So this is B and this is F. So here, it's just a special case. We were able to reduce the size of the multiplexer to 2 to 1 without any extra cost, However, for other functions, you might need, for example, an OR gate or XOR gate or XNOR gate. Depends, 2 input. In other words, you will have some function here in terms of the remaining variables, which are B and C, Okay. So this is method number 2 and method number 3 and so on. Of course, we can't reduce the size of the max to 1 to 0 max. There is nothing like this. So the smallest size we can go for is this. However, if we have a function of 5 variables, yeah, we can go from 32 to 1 max down to 2 to 1 multiplexer. Okay, any question? Now, there are many problems in the homework, not many, 2 problems, I guess, that are related to this topic, which is implementing logic functions using multiplexers. And in the worksheets and the practice questions, there are also other problems that you can practice, use them to practice. Okay, let's try to finish the last thing in chapter 4, which is basically the demultiplexers. Or Dmux. So basically, this is the last example that we want to consider regarding the functional blocks. And functional blocks, we said, basically are combinational logic circuits that are already designed for you, available for you to use without redesigning them. And this circuit, which is the demultiplexer, basically has a relation similar to what we discussed when we talked about the decoder and the encoder. The decoder and the encoder, they work in, they reverse the operation of each other. The same thing, the demultiplexer is a circuit that reverses the operation of the multiplexer. So what is this circuit basically? This circuit has a single input. So everything is mirrored, similar to the relation between the decoder and the encoder. The multiplexer has one output and n inputs, okay, or 2 to the power n inputs. The Dmux has one input, and a set of outputs. Output 0, output 1, output 2, up to output 2 to the power n minus 1. And what does this circuit do? What does the multiplexer do? Basically, the multiplexer takes as 1 out of 2 to the power n inputs and pass it to the output. What does the Dmux now do? The Dmux basically takes the output, the value that comes, the value that is received or that appears on the single input. There is only one input here. There is only one input, and pass it to one of the outputs. So we as users can select which output to pass the input to. So it is the opposite of the mux. The mux takes one of these values and pass it to the single output. The Dmux takes the single input, and you can select to which output to pass the output, this single input to. So in order to do that, we need to specify the output number. So we need, similar to the mux, we need certain number of selection lines, which is basically this is n selection lines. And here we have 2 to the power n outputs. So the relation between here and here is log. So we have 2 to the power n outputs, so we need n selection lines. However, the operation is the opposite of the mux. You take the value here, there is only one value here, you give it to this output, or this output, or this output, or this output. And how do you select the output? How do you specify the output? Basically using the selection lines. So if we call this input, we call this output. Let's see an example, or let's write what is, let's see an example to save time. What is the smallest Dmux? 1 to 2 Dmux. It is 1 to 2 Dmux. The smallest mux is 2 to 1. The smallest Dmux is 1 to 2 Dmux. So it is a circuit that has one input, I, it has output 0 and output 1, and it has one selection line. So this is 1 to 2 Dmux. And how does this circuit work? Basically, if S equals 0, then output 0 is I. If S equals 1, then output 1 is I. And in this case, of course, output 0 has to be fixed to some value, either 0 or 1. So basically, if S equals 0, then we can say the operation of the circuit, output 0 is input, while output 1 is, for example, 0. We can fix it to 1, but it's okay. You can pick whatever you want. If S equals 1, then output 0 is I, or sorry, is 0, and output 1 is I. So the output, the input passes to the output specified by the selection line. So we want to design this. So let's write the truth table. We have two inputs, S and I, and we have two outputs, output 1, output 0. So this is 0, 0, 0, 1, 1, 0, 1, 1. So as long as the input is 0, the output 0 is basically I. So this will be 0, 1, and output 1 is not affected by I, so it is 0. While as long as S is 1, then output 1 is the same as the input. So it will be 0, 1, while this will be 0, 0. So simply, this is the truth table of the 1 to 2 Dmux. So what is output 0 as a function of S and I? there is only one min, then there's only one, so there is no need to simplify. What is this? It is S and I. It is min term 3. Same thing for output 0. There is only one. There is no need to draw a K-map to simplify the function. So what is this? This is min term 1, which is S bar I. In min term 1 here, it is S bar I. So this is basically the logic expressions for the 1 to 2 Dmax. Let's draw the circuit. We have S bar, and here we have I, and here we have I. And this is output 0, and this is output 1. So this is basically the logic circuit or the logic diagram of the 1 to 2 demultiplexer. So you can put it in a box like this. So this is 1 to 2 Dmax. How about 1 to 4 Dmax? Same thing. You need to put the truth table, but however, the truth table will be very big. It will be, it will have how many? 1 to 4 Dmax. We will have how many inputs? The input and the 2 selection lines. For 3 inputs, you can still put the truth table. How about 1 to 8 Dmax? Still, it is manageable. You have 1 input, data input, and you need 3 selection lines to select one out of the 8 outputs. How about 1 to 16 Dmax? Here comes the problem. Because you will have 5 variables, 5 input variables. The input I and 4 selection lines to select one out of the 16 variables. However, you don't need to go this way. In other words, to design bigger demultiplexers, can we design a bigger multiplexer in an easier way without using a truth table? Yes, we can do that if we look carefully at this circuit. This circuit, we should be familiar with this circuit. What is this circuit? This is what I wrote here, it is 1 to 2 Dmax. However, it also looks like something that we already saw before.
1 to 2 decoder?
Exactly. It is 1 to 2 decoder. هيو. It is 1 to 2 decoder. هاد هيو بالأحمر. With output enable. لاحظ هدول ايش هم؟ لما جبنا احنا 1 to 2 decoder and we used 2 AND gates and we used here the enable, if you remember. This is a 1 to 2 with output enable. 1 to 2 decoder with output enable. So the Dmax is basically also a 1 to 2 decoder with output enable. Such that the data line of the Dmax is connected to the enable circuit and the selection line of the Dmax is connected to the address line. So basically, this is the address input of the decoder, and this is the enable input. This is where we enable the outputs of the decoder. So لو بدي أسوي example 1 to 4 Dmax, I don't need to do all this. I don't need to أحكي له Dmax, 1 to 4 Dmax is basically a 2 to 4 decoder. هو عبارة عن 2 to 4 decoder such that the address lines هم مشبوكين مع selection lines والenable تبع الديكودر هو basically الداتا اللي داخله. فراح اروح اجيب decoder. هذا decoder A1 A0 if you remember هون في enable وهون D0 وهون D1 D2 D3 1 2 3 4 هذا ديكودر بس I can use it as a 1 to 4 DMux by simply الانيبل اشبكها مع الانبوت والA1 والA0 هم basically S1 S0 وهدول هم output 0 output 1 output 2 output 3 فif I do it this way هذا basically صار my 1 to 4 DMux basically انا من خلال السلكشن لاينز بسمح لهذا الانبوت اما يظهر هون او يظهر هون او يظهر هون او يظهر هون عشان هيك اذا بتروح اليوم بتدور على اي سي رقمها 74LS138 او اي اي سي that contains a decoder a line decoder راح تلاقي جوا الاي سي على جوا الفايل اللي بوصف هذه الانتجريتد سيركت التايتل او اسم الاي سي اسم السيركت اللي موجوده داخل هذه الشيب راح تلاقي انها مثلا دائما بكتب لك decoder / DMux اي circuit that implements a decoder with output enable can be used a demultiplexer by simply changing or wiring it up بالطريقه اللي حكينا عنها. الانيبل هو مشبوك مع الداتا تبعت الديماكس والسلكشن لاينز تبعت الديماكس مشبوكه مع الادرس لاين تبعت الديكودر. اي اي سي that implements a decoder هي basically IC that can be used as a demultiplexer. So we don't need to do all this if we want to design bigger demultiplexers. All right, we have a bit more than 10 minutes. Let's go to the e-learning to take our fourth quiz. خليني بس اروح على الاي ليرنينج انا كمان زيكم.